Hello, everyone. Welcome back. So we are now going into our second unit. So we've covered Unit 1, which is basically the geological side of oceanography, and now we're moving on into our second unit. So our second unit is divided into kind of two somewhat separate topics in a sense, where we're going to do chemistry of water and seawater, but don't worry, we're not going to do like anything crazy and like blow things up or anything like that. And then we're also going to focus on the atmosphere and climate change. So this unit is going to cover chapters 4, 5, 6, and chapter 16. So chapter 16 is the climate change chapter in your book. So we're just jumping ahead for a second, and then we're going to come back and go into chapters 7 through 14 or 15 after we cover this. So that's a common kind of scary sort of thing, but don't worry, it's there for a reason. It's not a typo or anything. So just a little heads up with all of that. So just some kind of general reminders as well is that you have your first exam is available for you to complete as early as this morning, and it is due on Sunday at 11:59 p.m. It will completely shut off at 11:59. So if say you start it at 11 and you don't finish it, it's going to kick you off at 11:59. So that's just a thing that happens there. And just a reminder that the initial score that you're going to see in Canvas is not going to be the complete score yet. I still have to go through and grade the short answer questions and your calculation, and don't worry, I have all these things manually tagged for me to look. So don't freak out, it'll be all right. Okay? Please holler if you do have any questions or comments or concerns or any sort of tech issue that may arise, but it happens. Technology always loves to fail at the most inconvenient times. So all that said, let's go on ahead and get into our material for the rest of for the start of this. So this would be lecture 9. So we're going to talk first. We got to break down this idea of water and what the heck is water. What is it made out of, and the various bonds that exist between the molecules that make up water. And that's a very, very important thing. So water, as you can probably imagine, is extremely important for our planet, right? We're mostly water. Our human body is mostly water. We need water to survive, right? But water has some really, really interesting properties that make our planet as unique and wonderful as it is. So going into it. So our water molecules are consisted of hydrogen and oxygen. Perhaps you've heard someone call water H2O, or if anyone has seen the movie Waterboy, that is some high quality H2O. And if you've never seen Waterboy, you're missing out on an Adam Sandler classic. Anyway, so there's this bond between the hydrogen and the oxygen atoms of the same water molecule. This is a very important thing to keep in mind. Of the same water molecule is a covalent bond, and that is an insanely strong bond. Like, it's more strong than anything that you could imagine, pretty much. So with that, then this is kind of looking at the electron rings here. Kind of gets like some Mickey Mouse vibes over here on the right hand side, right? And so the two hydrogen atoms are on the same side of the oxygen atom, and this makes the molecule dipolar, which is a pretty important difference, say, between like carbon dioxide, which is actually a straight line of those atoms, whereas with water, it's polarized, or it's dipolar. So because of that, then we have some excess negative charges on one side of the oxygen and excess positive charges on the other side of the hydrogen atom, and that's what this bottom graphic is making an attempt at showing. So the reason why that is so important is because when we're considering the bonds between other molecules, like say other water molecules that that polarity difference is really, really important here. So that's what this is trying to show here. So we have covalent bonds, ultra, mega, super, super strong. And then, so that's between the hydrogen and oxygen of the same atom. And then next we have hydrogen bonding. So hydrogen bonds are still very, very strong, but not as strong as covalent bonds. So these are a little bit easier to break. So because of that polarity, right, that slight positive charge at the end of the hydrogen and the slight negative charge at the end of the oxygen, that gives us the attraction then between the positive and the negative ends of those water molecules to each other ions. So water can bond to a lot of different ions or different molecules. Just, you know, bonding to its own is really quite fascinating. And again, because of the polarity differences between the hydrogen and the oxygen. So covalent bonds are between hydrogen and oxygen of the same atom. Hydrogen bonds are the hydrogen and oxygen of other water molecules. All right, so that's a pretty big difference between the two there. And there's some really interesting properties with hydrogen bonds that make water extremely unique. So even though hydrogen bonds are weaker than covalent bonds, they're still so strong that they result in high water surface tension, high solubility of chemical compounds in water, which basically means that you can break down other things in water. Like if you put salt in water and you give it a little stir, the salt breaks down and makes salty water. Or if anyone here has the lovely task of making simple syrup, if you work in a restaurant or in a bar or something like that, then that you know that you just mix sugar and water equal parts, and that breaks down into simple syrup, hence the name simple syrup. So you can even think of things like erosion, right? Like even though water is one of the softest things on the planet, it is hard enough that it can carve out an entire Grand Canyon, for example. So it can do a lot for erosion and things of that nature as well. There are also some really unusual thermal properties of water, meaning that it takes a ton of energy to change the temperature of water, whether or not you're cooling it down or warming it up. And lastly, there's the unusual density of water. So we'll get to that here in just a second. So I want to go into details of these components that make water so unique. So starting with surface tension, I have a couple of pictures to kind of show it. Maybe you've done this experiment before or an experience similar to this, maybe in like, I know it sounds kind of silly and rudimentary, but maybe in like elementary or middle or even high school, and you have like a little pipette or a little dropper, and you try to drop as many drops of water on a quarter without it spilling out. Maybe you've done that before, so that creates like this huge bubble around the quarter or penny. Is kind of fun. But here are just some pictures to kind of help show that. This is a cute little jaguar, probably going in for a kill, going for a hunt. But notice how the water is pretty much bubbled around the whole face. And don't you want to boop that little snoot? It's so boopable. But because of that high surface tension, you know, the only things poking through here are his whiskers. Or here's even another very boopable snoot of a cute little shark, right? So see how the water is going over the shark's nose and the nose isn't penetrating through? That's surface tension. And then here's maybe if you're into water sports or just sports in general, this is someone kind of trying to swim through the water, right? So it makes you a little bit more aerodynamic, you know, things like that. So that's just showing the high surface tension of water, which is really quite fascinating. And that will come into play in terms of like waves and you know, keeping things rather contained rather than just kind of floating around willy-nilly. This next idea I want to bring about is the the thermal properties of water. And before we do that, we just got to remind ourselves what some of these definitions are. So take a moment to think about the word heat and the word temperature and what exactly those mean to you. Maybe do a little pause of this video real quick and think about what those words mean to you. What comes to mind? You know, what's the first thing you think of when you hear those two words, heat and temperature? So heat is officially defined as the amount of energy that moves from one object to another object. And that's all thanks to temperature contrasts, by the way. And the general rule here is from hot to cold, which you're like, what? For real? If you take your hands, which are warm, and you set them on the desk in front of you or on your maybe laptop is not a great example because the laptop's warmer, but something that's cool around you, the heat that is transferring from your hand to that colder object. Another weird kind of analogy to think of is if you have an ice drink, like an iced soda or an iced water, your beverage is actually warming up the ice. The ice is not cooling down your drink, which is kind of weird to think about, right? Like say you have a cup of tea or a cup of coffee that's really super hot but you really want to enjoy it right now. Well, yeah, and you like want to put an ice cube in it. Well, you're not putting the ice cube in it to cool it down. Your hot drink is actually warming the ice cube up. Kind of you're like, oh, what? Yeah, totally real. Next up, we have temperature. So temperature is defined as the amount of heat an object has, and this is related to the kinetic energy and motion of atoms. And I also want you to think to yourself, does a warmer object's atoms move faster or slower than a colder object? Think about it, pause, take a moment. Warmer objects' atoms move faster. They vibrate at a much faster rate than colder objects. Last thing in terms of temperature real quick is the unit of measurement that we use for temperature. There's three main ones that we use. So think about it, maybe pause again, think about which units are used to describe and define temperature. And here we are. So we have three main units. We got Kelvin, which is what we use in science. We got Celsius, which is what's used everywhere else but here in the United States. And then we have good old Fahrenheit, which is here for us. So I just have the equations for temperature conversions. We're not going to worry about that in this class. I just have them provided here for you just in case you had any desire. And then this is just a table showing, comparing the different temperatures across the board. So say, for example, 100 degrees Celsius is the boiling point of water, but 100 degrees Celsius is the same as 212 degrees Fahrenheit. So that's where water boils. Our average body temperature is about 98.6 degrees Fahrenheit, which is 37 degrees Celsius. And the melting and freezing point of water is 32 degrees Fahrenheit or 0 degrees Celsius, which is 273 degrees Kelvin. So the only value that goes to absolute zero is Kelvin, and that's the coldest thing in the known universe. What's kind of funny is the only time where Celsius and Fahrenheit overlap is at -40. Everything else is a bit different there. So this is just, a reminder of what temperature and heat are. So in the next video, we will go into further ideas of water and the properties of water and why that is so important. So thank you so much for watching the first one.